Statistics of random square tile surfaces, Part 2. In this talk, I will go into more detail about what entails improving the theorems. I will assume that you've watched the previous video and I won't recall the notation, but let me just recall some key things from the previous talk. Recall that the randomizing model we are using for n square tile surfaces is Sn cross Sn. Recall that the genus theorem said that the expected genus has a linear growth n over 2 with precise second order and constant terms. And recall that the holonomy theorem gave information on holonomy sets of random square tile surfaces. In particular, it said that the probability of your surface having exactly the relatively prime vectors of z2 as its holonomy set goes to 1 over e as n goes to infinity, and the probability of a surface containing the relatively prime vectors as its holonomy set goes to 1 as n goes to infinity. Now let's start off by learning how to use the model. The first lemma I want to talk about is the vertex clearing lemma or observation that tells you when two vertices are two square corners are glued. Given a square tile surface with sigma and tau as the horizontal and vertical permutations, square I and j have their bottom left corners glued if and only if I and j are in the same cycle of the commutator of sigma and tau. Let's see how one goes about proving this with a simple case. Here I've assumed that I'm going to assume that j immediately follows I in the cycle, and we'll see how that gives you that I and j have their bottom left corners identified. The idea is very geometric, so let's just carry out the action of the commutator. So first, tau inverse of I is glued to the bottom of I by definition. Then we have sigma inverse tau inverse of I glued to the left of that. Subsequently, tau sigma inverse tau inverse of I is glued to the top of sigma inverse tau inverse of I. And since I've assumed that j is the commutator times I will now have this edge, red edge over here, glued to the left of j, okay, which really means that this corner here is glued to this corner, and so I and j have their bottom left corners identified. And similarly, you can work the other way around as well. Now the upshot of this is that the number of vertices is equal to the number of disjoint cycles of the commutator, because every vertex has a representative that is the bottom left of a square. And not only that, this lemma gives us a little bit more. You can actually deduce the angle around the cone point by knowing the length of the cycle that the corresponding square is in. So for instance, if I was actually a fixed point, in which case I is equal to j, then what you would get is this edge, this red edge, which I'm now going to label green, will be glued to the left of I, right? So this would close up, which means that the angle around this vertex is in fact 2 pi. Okay, and so that vertex is actually not even a cone point. It's just a regular point. It just happens to be a square corner, or it happens to be a vertex. End of the gluing. And so fixed points correspond to these non-cone point vertices, which will be important in a bit. Okay. And you can kind of generalize this. If the cycle length was 2, then you went around twice, so your cone point had angle 4 pi. Okay. The next lemma that I want to talk about is the holonomy characterization lemma, which is giving a combinatorial condition for a square tiled surface to be a holonomy torus. Okay. Given a connected square tiled surface with n squares, with horizontal and vertical permutations sigma and tau, respectively, such a surface is a holonomy torus if and only if the commutator is fixed point free. And the intuition is as follows. Okay, so S is not a holonomy torus. So this happens if and only if there exists W, which is in Z2 minus RP, intersect holonomy set. And that happens if and only if there exists a non-cone point vertex, like the one we discussed earlier, in the saddle connection that realizes W as the holonomy vector. Okay, and that should correspond to, that non-cone point vertex should correspond to a fixed point, if and only if there exists a fixed point of the commutator. Okay, so that's basically the idea, almost the entire proof of this lemma. The next lemma is the combinatorial visibility lemma, which is giving a combinatorial characterization or condition that ensures that a square tiled surface is visible, or visibility torus. A square tiled surface, with n squares is a visibility torus if commutator has less than n over 2 cycles. Okay, and the intuition is similar, although the proof is slightly different, and I don't want to go into it too much. It uses the SL2Z action, which is kind of neat, and you can definitely ask me in the comments, and it's fairly easy to explain, but I'm not going to go into it. The intuition really is that if you have less than n over 2 cycles, then you don't have that much space for fixed points in your commutator. So that means you don't have that many non-cone point vertices, right? So most of the square corners that appear are going to be cone point. So you're more likely to capture all the primitive Z2 vectors. Okay, so it's sort of related to the holonomy characterization lemma, but a little bit different. Now the takeaway of all 3 of these lemmas is that if you want to know anything about the geometry and topology of square tiled surfaces, then you must care about the cycle statistics of commutators because of this combinatorial connection. And so this motivates the key lemma that we're going to use, and the slogan for for this lemma is that the commutator distribution is asymptotically uniform. Okay, and I'll explain what that means. Make it more precise in a bit. So to set up notation, let omega sub n be a map from Sn cross Sn to the alternating group, right, which takes a pair of permutations and evaluates its commutator. Now the commutator is always going to be in An, and in fact, it's classically known that every element in the alternating group is a commutator for large enough n. So using this word map, or commutator word map as I like to call it, we can push the uniform distribution on Sn cross Sn, which is the random model, to a probability distribution on the alternating group, defined as follows. Okay, so here P sub W sub n is the probability distribution on An, and so given any element pi in An, the measure, the probability measure says that you want to count the pre-images under this map and normalize it appropriately. Okay. The key lemma then is that the probability distribution on An that you have just obtained is not far from the uniform distribution on An, and in fact, asymptotically they are the same. One converges to the other in total variation distance, which I've defined over here. To approach the proof of this lemma, we will use some representation theory. So here's just a dash of representation theory to recall, just to keep this talk self-contained. And I won't develop representation theory in the most general case, just in the case, in the setting that I need for my proof. So let G be a finite group and V a complex vector space. A representation of G is a homomorphism from G to the general linear group of V. And heuristically, what you should think about is that a representation is capturing the information of a group acting on a vector space. Okay, the action of G on the vector space is what the representation is. The dimension of a representation is just the dimension of V, the vector space, and the character of a representation is this function chi from the group to the complex numbers, which takes the trace of the representation. Okay, so you get a matrix in GLV from the representation, and you just take the trace of that. A Fourier transform of a probability measure P at a representation is this sum here, and it's a generalization of the discrete Fourier transform, but also you should think about this as, if there were a 1 over, the size of G here, you should think about this as averaging the representation over your group with respect to this probability measure. Okay? And the reason we study this, Fourier transform is motivated by this next lemma. And this lemma is by Diaconis and Shasahani. And what it says that, if you have P, a probability measure, and U, the uniform measure in G, then the total variation distance between the probability measure P and the uniform measure is bounded above by this expression that's in terms of the Fourier transform of the probability measure. Okay, and this star is just the complex conjugate, and dimension is the dimension of the representation, and you're summing over the irreducible representation. So G hat is the set of irreducible representations, we are now ready to sketch the proof of the key lemma, the commutator distribution lemma. And the starting point is the Diaconi/Shahani lemma applied to our case for an. And when you apply it carefully to the case for an, what we get is this upper bound here, that the probability measure that we care about, induced by the commutator map, is different from the uniform measure on an by at most this quantity right here, which, now you're summing over the irreducible representation of Sn, not an. And in terms of the Fourier transform. Okay, so it's something technical, but it turns out to be very useful. Frobenius next gives a classical formula for this probability that we have induced by the commutator map, right? And it's given in terms of this character theory of Sn, so summing over the irreducible characters and this expression here. Then what you can, doing some work, you can show that the Fourier transform, is this very simple form now. With some algebra and using this formula by Frobenius, you get even a diagonal scalar matrix. And plugging this information in finally to that upper bound gives you great control and simplifies it greatly to this expression here. And then you use a result by Liebig and Shalev, which tells you exactly how this is growing, or gives an upper bound on how this is growing asymptotically, which converges to 0. And we're done with the lemma. The upshot of this lemma is that the cycle statistics of commutators are approximated by the cycle statistics of permutations in an as n goes to infinity. Okay, so the big picture really now is, if you cared about the geometry and topology of square-tiled surfaces, the randomizing model told you that the cycle statistics of commutators of pairs in Sn is the stuff that you need to be caring about. And this key lemma tells you that, in fact, you can get away with just knowing information about the cycle statistics of uniform permutations in an, okay, to obtain geometric and topological information of square-tiled surfaces. So now all it remains is to get information, get some key facts about the alternating group, and invert it in the square tile land. So let me end by giving you a glossary of facts from the alternating group. The first fact is that the density of fixed point free permutations in an converges to 1 over e. And it's actually fairly easy to see this. What you do is you start with any letter from 1 through n, or any number from 1 through n. Then the probability of a permutation fixing it, or an even permutation fixing it, doesn't matter, is 1 over n, because there are n minus 1 factorial permutations fixing it, and total, or n minus 1 factorial over 2 even permutations fixing it, and n over 2 factorial permutations in total in an. So the probability of a permutation not fixing it is 1 minus 1 over n, right? So if you wanted the density of fixed point free permutations, you should be not fixing any of the, i's. So density of fixed point free permutations should be 1 minus 1 over n for each of the letters 1 through n, and this converges to 1 over e just by calculus. So that's pretty straightforward. What this means for square tile surfaces is that the density of holonomy tori converges to 1 over e, and that's because of the holonomy characterization lemma that we had earlier. Similarly, another fact that comes into play is that a generic permutation in the alternating group has less than n over 2 cycles. Now what I mean by generic is that asymptotically almost surely as n goes to infinity, an even permutation has less than n over 2 cycles. And because of the combinatorial visibility lemma, what this means is that a generic square tile surface is a visibility torus. A third fact that comes into play is that the average number of cycles of permutations, even permutations, is this expression here, where the first part is just the nth harmonic number and there's a correction. This expression, is equal to log n plus gamma plus like some error term. And this is exactly where like the Euler-Mascherani constant comes from. And what this means for us is that the expected genus of a random square tile surface with n squares is n over 2 minus log n over 2 minus gamma over 2 plus 1 plus something that decays to 0. And that's because of the Euler characteristic formula, which is 2 minus 2g is equal to v minus e plus f, number of vertices minus edges plus the number of faces. And since we are fixing, n squares, f is fixed to be n, e is fixed to be 2n, and hence you just care about the vertices, which, as you know, because of the vertex gluing lemma, is roughly log n plus gamma plus little o of 1. And hence, solving this, you get the genus to be n over 2. And so these are just 3 facts that are relevant for the theorems. One could imagine, deducing other facts about alternating, like even permutations, and carrying it over to square tile land. For example, the average number of fixed points gives you information about the average number of cone points in square tile surfaces. Similarly, the distribution of normalized cycle lengths of permutations in AN gives you distribution in the strata of square tile surfaces. And actually, because of that, that the square tile surfaces distribute in the strata according to the Poisson-Dirichlet distribution, in the limit. So there are some deeper things going on, but for the purpose of our talk, these are the 3 facts that are, relevant. Thank you for listening to my second talk. Please leave me comments, feedback. Hope you enjoyed it.